Hello, and welcome to the last module of Unit 4 covering the polarization of light. Recall that an electromagnetic wave is composed of an oscillating electric field, which is perpendicular to an oscillating magnetic field. The two fields are in phase and oriented perpendicular to both each other and the direction of propagation. The polarization of an electromagnetic wave is defined to be in the direction of the electric field. A beam of light is comprised of many electromagnetic waves. Each individual wave can have a different polarization. So if the polarization of the rays is random, then the light beam is said to be unpolarized. Unpolarized light is often represented by electric field vectors radiating outward from the axis of propagation. But remember, unpolarized light is actually a beam of many oscillating electromagnetic waves that have both an electric field and a magnetic field. Light that starts out unpolarized can be polarized using a special filter. This filter will dampen out any rays in the beam that are not polarized in a certain direction, decreasing the intensity of the original wave by 1/2. In Unit 1, we learned that the intensity of a wave is proportional to the amplitude of the wave squared. This is true for electromagnetic waves as well. In fact, the intensity of an electromagnetic wave is just the maximum amplitude of the electric field squared. This means that the unpolarized intensity of an electromagnetic wave is just I equals E0 squared. Once the unpolarized light is filtered, both the intensity and the maximum amplitude of the electric field are reduced. You can send light through a series of polarizing filters. If light has already been polarized in one direction, sending it through another polarizing filter will polarize the light in the new direction. If the second filter polarizes light in the same direction as the first filter, the intensity does not change. If the second filter polarizes light in a direction perpendicular to the first polarizer, the intensity goes to 0. However, if the second filter is at some angle theta to the first, the intensity of light decreases by an amount that is dependent on the cosine of the angle theta squared. Let's do an example. Suppose that light, which is originally unpolarized, passes through a polarizing filter that has an angle of 30 degrees to the y-axis. That light then passes through another filter, which is at an angle of 60 degrees to the y-axis. The light passes through a third filter, which is also at an angle of 60 degrees from the y-axis. Finally, the light passes through a fourth filter, which is angled at 80 degrees from the y-axis. If the original intensity of the light is 100 watts per meter squared, what is the final intensity of the light after going through the fourth filter? So I'm going to go ahead and label the intensity at each stage of this problem, and I'm going to label my intensity with subscripts that match my angles. So this is I1. After it passes through the second filter, we're going to call it I2. After it passes through the third filter, it'll be I3, and then I final or I4 is after it passes through the last filter. So starting with the original unpolarized light, I0, which is I unpolarized. When it goes through the first filter, it actually doesn't matter what the angle of the filter is. We know that when it goes from being unpolarized to polarization at some angle, the formula that we need to use is that I1 equals 1/2 I0. So this gives us I1 equals 50 watts per meter squared. When the light passes through the second filter, it has already been polarized. So now we have to use the other equation. We're going to use I2 equals I1 cosine squared of theta. Now what is theta? It's the difference between the angles of the two polarizers. So this gives us I2 equals 50 watts per meter squared times the cosine squared of 30 degrees. So now that we have I2, let's tackle what happens when light passes through the third filter. The second filter is oriented at 60 degrees from the y-axis, and the third filter is also oriented at 60 degrees from the y-axis. Since these two filters are at the same orientation, the same angle from the y-axis, the light will not lose any intensity as it passes through the third filter. You could see this by realizing that theta 3 minus theta 2 is 0 degrees, and of course cosine of 0 degrees is 1. So we would end up getting I3 equals I2 cosine squared of 0, or I3 equals I2. Moving on to the fourth filter, theta 4 is 80 degrees and theta 3 is 60 degrees. So the difference in angle between these two filters is 20 degrees. So we're going to use the equation I4 equals I3 times the cosine squared of 20 degrees. Plugging all this in, we find that the final intensity, I4, is equal to 33.11 watts per meter squared. Light can also be polarized when it reflects off of a refractive surface. We saw that when light hits a refractive medium, some of the light reflects and some refracts. The intensity of the reflected and refracted rays were depicted in the PhET simulation bending light as more transparent rays. This loss of intensity accompanies the polarization of reflected and refracted light. The reflected light becomes partially polarized in a direction parallel to the surface of the boundary between the two media. The refracted light also becomes partially polarized along the reflective plane. The reflective plane is the flat, two-dimensional surface that contains all three rays. If light is incident on a boundary at a very steep angle, meaning at a small angle of incidence, both the reflected and the refracted light are only partially polarized. However, when the angle between the reflected and refracted light is equal to 90 degrees, the reflected light will be completely polarized in the direction that is parallel to the surface. This is called linear polarization. The angle of incidence that corresponds to this special case, when the angle of reflection and the angle of refraction are 90 degrees relative to each other, is called Brewster's angle, written theta sub b. Okay, so this is a lot of angles. Make sure you are clear here. When the reflected and refracted light are at an angle of 90 degrees from each other, the angle of incidence is called Brewster's angle. Of course, since the angle of reflection is always equal to the angle of incidence, this means that the angle of reflection could also be called Brewster's angle. You should pause this video and study the diagram to make sure you understand the relationships between these three angles when the reflected light becomes 100% linearly polarized. When light is incident at an angle greater than Brewster's angle, the reflected light is still linearly polarized. So Brewster's angle is a minimum angle at which light is linearly polarized. There's an easy formula to find Brewster's angle. The tangent of Brewster's angle equals the index of refraction of the refracting medium over the index of refraction of the incident medium. Be careful, this is very similar to the equation that we saw for the critical angle, which, as you recall, is the angle at which light is 100% reflected. But the difference between the sine of theta and the tangent of theta will give you very different angles. Most of the light that we see when we are outdoors comes from the sun's rays, either directly from above or after they have reflected from some object or the ground. Since reflected light tends to be more linearly polarized, this means that much of the light we see when we are outdoors is linearly polarized to some degree. This explains why sunglasses are usually vertically polarized, to reduce the amount of horizontally polarized light received by the eye, and thereby reducing much of the glare of sunlight bouncing off of the surface of the Earth. In summary, the polarization of light is defined to be in the direction of the electric field. When light passes through a polarizing filter, its intensity decreases according to the equations I filtered equals 1/2 I unpolarized if the original light is unpolarized, or I filtered equals I polarized times the cosine squared of theta, where theta is the angle between the initial polarization and the polarizing filter. When light hits a boundary between two refractive media, the reflected light becomes partially linearly polarized and the refracted light becomes partially polarized along the reflective plane. The angle at which reflected light becomes 100% linearly polarized is called Brewster's angle, which can be found with the formula tangent of Brewster's angle equals the index of refraction of the refracting medium over the index of refraction of the incident medium.